Good morning. I'm Saritha Kumari, Assistant Professor, Civil Department, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Under the course Performance of Transmission Lines and Cables, today the topic is when transmission line terminated through a resistance, what is the behavior of the travelling waves? This is mapped to course outcome 4. So, we see the diagram here on the right side. So, the transmission line, this is a transmission line, okay. So, whose input voltage, sending end voltage is V. So, and we also know that the line having its natural impedance ratio of the voltage by current. So, which gives the transmission line impedance, okay, Z. And at the receiving side, the transmission line is terminated, it's having a value connected to a value resistance value capital R. So this is the case. We are going to look at the behavior of the travelling waves. So now here the first line, that is a point it is mentioned. The line is terminated. The line is terminated through a resistance capital R. Now in the previous sections, in the previous lectures, we have seen last two lectures. We have seen when a line is terminated with the open circuit, when the line is terminated with a short circuit, the value, what is the behavior? The behavior of the travelling waves. So we have seen. So here the main point is whatever be the value of terminating impedance, whether it is open circuit or short circuit, the one of the voltage or current waves is reflected back with negative sign. Okay, we have seen. Okay, either voltage or current wave is reflected back with negative sign. Also here we know that the reflected wave travels along the overhead line along which the incident wave is travelled. Okay, through the same transmission line, whatever the input, input voltage and current wave, that is incident wave travel. So after reaching the other end, receiving end, the reflected wave, so when it is a open circuit or short circuit, so then this voltage wave and current wave, they travels back, through the same line. So therefore the relations are given for the voltage and current waves. Okay, so I dash is equal to minus V dash by Z. Okay, I dash is equal to minus V dash by Z. Where we know that what is Z? That is a line impedance. Okay, line impedance. Now, what are the I dash and V dash? What are the I dash and V dash? They are the reflected voltage and current waves. Okay, so just remember, we know that V and I are the input sending voltage and current wave. Okay, that is also called incident wave. V dash and I dash are, V dash and I dash are reflected voltage and current wave at the receiving end. Okay, at the receiving end. Okay, when they are open or short circuit. Now the refracted wave or transmitted wave is given by already known this sum of the incident wave and reflected wave. Now consider V double dash and I double dash are the refracted voltage and current waves. Okay, just remember V double dash and I double dash are the refracted voltage and current waves into the resistor. Okay, so at the receiving, where is the resistor? At the receiving end place. So we know that. So at the receiving end now, the total value of voltage and current is called, that is refracted or transmitted wave, which is given by sum of the incident wave and reflected wave. So let us say those refracted voltage wave and current wave are V double dash and I double dash. Now, okay, already we know what is, okay, V and I. They are the incident waves. Now, the following relations are poles from the idea of this relation. Okay, so we know that. So the three relations are current equations in terms of voltage and impedance. Okay, our resistance is written. We know that for the incident wave, from the incident voltage and current wave, I is equal to V by Z, and for the reflected wave, I dash is equal to minus V dash by Z. Okay, so because either one of voltage or current wave is reflected back with negative sign, that's why we have minus already. Okay, I mentioned this just now. Now, what is refracted? For the refracted wave, the relation between voltage and current is, okay, that is at the receiving end. So at the receiving end, we mentioned that the line is terminated with resistance value R. So the I double dash is given by V double dash by R. Now using the relation between refracted wave, incident wave and reflected wave, I double dash is equal to I plus I dash. Okay, refracted current wave is equal to incident wave plus reflected current wave, and similarly for the voltage wave also, V double dash is equal to V plus V dash. Now using these relations, we substitute the above these equations. So in the current equations, okay, if we consider in the current equation, so what is I double dash? That is given by V double dash by R. I is V by Z. I dash is V dash by Z. Now take LCM before that, written V dash, okay, V in terms of V and V double dash. So we know that V dash can be written as V double dash minus V. So after simplifying this, what is V double dash? It is given by 2VR by Z plus R. See, this one is equation 1. Okay, just numbering is given for the finally we are going to use these equations. So say this is a V double dash equation in terms of V is equation number 2. Now similarly current, okay, refracted current is given by I double dash. Okay, so because we can write this V double dash by R is nothing but from this equation 2. What is V double dash by R? That is I double dash. So that is nothing but 2V by R plus Z. So multiply and divide with Z. Okay. Now because we want I double dash only in terms of I. Okay. In terms of I in terms of R and Z. That's why in numerator and denominator multiply and divide with Z. So finally I double dash is given by I into 2Z by R plus Z. So this is V double dash I double dash. Okay. Now say that equation number 3. In a similar manner we derive the equations for V dash and I dash also. Okay. So now use this equation 1. So in equation 1, substituted in place of V double dash. Substituted in place of V double dash. Okay. So in terms of V and V dash. So simplify this. We get the equation for V dash in terms of V. In terms of V. Okay. So V dash is given by V into line parameters, line constants, okay, R and Z, that is R minus Z by R plus Z. Similarly, okay, because we know that this is V dash, I dash is V dash by minus V dash by Z. So already this is a V dash. So substitute here for V dash. What we get? Okay, V by Z. Okay, V by Z into minus V by Z into R minus Z by R plus Z. So these are the equations for V dash and I dash. Okay, now from these relations, say about the coefficient of refraction, okay, for current and voltage, and also coefficient of reflection. Okay, so from these equations, what is a coefficient of refraction? Previously we have derived, previous slide, V double dash and I double dash. So coefficient of refraction for current wave means I double dash by I. Okay, so I double dash by I. So that is what? 2Z by R plus Z. So that is what it is, coefficient of refraction it is called. Okay. Now similarly for the voltage. So same thing already derived. So that is 2R by V double dash by V. 2R by R plus Z. RZ plus R. Now coefficient of reflection. Coefficient of reflection is for current wave, first I dash by I. Okay, so this is nothing but this is I dash by I, right? So we know that here this is nothing but what? V by minus V by Z is nothing but I. V by Z is I. So I dash by I is given by minus of R minus Z by R plus Z. Okay, so this is I dash by I. Coefficient of reflection for current wave, and similarly voltage wave. So coefficient of reflection for voltage wave. Okay, so coefficient of reflection for current wave. So it is given by plus R minus Z by R plus Z. Okay, now using these equations, we already derived, okay, in a standard manner. Okay, so now check once for the previous two sections. Okay, for the open circuit case and short circuit case. So first here for the open circuit, we know that at the receiving end it is open means current 0 means whatever the resistance value, line at the receiving and current 0 means resistance becomes infinity. Okay, so that is a open circuit. Okay, open circuit. So line resistance infinity. So for the coefficient of refraction for current wave, coefficient of refraction for current wave, it is given by using the relation 2Z by R plus Z. 2Z by R plus Z. So R place in R place substitute infinity, 1 by infinity 0. So for the open circuit case, so what is the current value? If we recollect, okay, whenever it reaches the receiving end, current, okay, voltage becomes twice and current becomes 0, right? That's why we say that current becomes 0 means current is reflected back with a negative value. So what is the total value of current? There 0. Now if we check for voltage, substitute in the equation 2R by R plus Z, R value infinity. Here it is simplified 2R by, okay, R plus, in R is there in numerator and denominator. So divide both numerator and denominator with the R. So it becomes 2 by Z plus R, 2 by 2, 1 plus infinity, 1 plus 0, Z by infinity means, okay, 1 by infinity 0, Z by infinity 0. So it is value. So that is how we can understand. Okay, we already know in the open circuit case, after voltage reaches the receiving end, voltage reflected back with again the same magnitude. So the total voltage becomes twice. Okay, so that is how we can explain, and current became 0. Next, similarly about the reflection, coefficient of reflection for current and voltage, we can check using the equation minus R minus Z by numerator and denominator. R is there, so divide with R both numerator and denominator. So it becomes 1 minus Z by R1 plus. So it becomes finally 0. So what is the value? Minus 1. So already we know this current is reflected back with the negative sign, that's why it is nothing but okay -1. Of course, coefficient of reflection is 1 unity only with the magnitude wise. Okay, for current wave it is -1. Similarly for the voltage, R minus Z by R plus Z. So same manner, if we okay divide with both numerator and denominator with R 1 minus Z, Z by R by 1 plus Z by R. So its values become 0. So what is the value? 1. So coefficient of reflection for voltage wave, in case of open circuit, it is 1. So voltage is reflected back with a positive, positive unity value. That's okay. So that is about the open circuit. It is already proved. It is proved now. Okay, so it is clear understanding. Now, similarly for the short circuit case. Short circuit case, of course, I am not showing the derivation like this. Okay, like for the open circuit, what we have seen. But okay, same equations we can substitute. For the short circuit case, current becomes 0 when the wave reaches the receiving end where it is short. Current is infinite. Okay, so current infinite means what is the resistance value? V by I. V by infinity. Okay, so resistance becomes 0. Substitute this in the equations. Okay, so check once again. Already we know short circuit case. Okay, the behavior of the both voltage and current base. Okay, voltage whenever it reaches the receiving end, voltage becomes 0. Okay, voltage becomes 0. That means it is reflected back with a negative sign. Okay, so their coefficient reflection is for voltage -1. For current it is +1. Okay, and what is the coefficient of refraction? For current wave it is 2. For voltage it is 0. So we can check similar manner using the equations. Okay, substituting this R value 0. Next, when line is terminated with a resistance value equal to natural impedance. Okay, if the line is terminated with a resistance value terminated value equal to line impedance, natural impedance. Okay, that is what R is equal to Z. So substitute this in the equations. So first, coefficient of reflection for current wave, the equation minus R minus Z by R plus Z. Substitute for R. Okay, so what is this? Z minus Z becomes 0. Similar manner for the voltage wave, R minus Z by R plus Z. Same, it is well again 0. So what does this mean? Coefficient of reflection for current wave is 0 and also voltage wave also 0. Okay, for the resistance value equal to natural. Now, what is the coefficient of refraction? Okay, so it maintained same value because reflection became 0 for both voltage and current. So the magnitude of total voltage is not going to change. So that's why it is proved here once again. Coefficient of refraction for current wave 2Z by R plus Z. Substitute R is equal to Z. So it becomes 2Z by 2Z1. And next, what about voltage? 2R by R plus Z. So it again becomes 1. So, okay, it is maintained same. Now, here there is a point. It is seen that the transmission line, when the transmission line terminated through the resistance value equal to such impedance, it does not suffer reflection. Okay, there is no reflection, and therefore such lines could be said to be of infinite length. Okay, such lines are said to be infinite length, and they are also called matched lines. They are also called matched lines. Okay, so just know this point. When the line terminated through a resistance value equal to surge impedance, that is Z, there is no reflection. There is no reflection in the line, and such lines they call it as such lines they said to be of infinite length, and they call the lines as matched lines. Matched lines, and the load corresponding to this is known as surge impedance loading. Okay, already we have seen this point previous. Okay, I think 2-3 lectures back. So when the line resistance, terminating resistance value equal to surge impedance, okay, the lines are said to be surge impedance loading. Okay, which is also called natural impedance loading. Natural impedance loading. Okay, so this is a point. Okay, these are the references for this lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.